Hello everyone. It's our pleasure to welcome today Cristiano Porciani for the seminar. Cristiano did his PhD at CSER and in Baltimore under the supervision of Matt Arez, and then did some postdocs in Jerusalem with Deckel and Cambridge, and got a Zwicky fellowship at ETH Zurich and then a permanent position. And after that he moved to Bonn as a professor. He's supervised about 16 PhD students and has just been offered, is that okay to say? Or just been offered a position at the Institute of Computational Cosmology in Durham. His main topic of research is large-scale structure dynamics, the IGM, and reionization. He's been working a lot on computing bispectrum in the recent past. And I'm particularly interested in today's talk, and I hope you will be too. So he's going to tell us about myths and truths about the halo formation in cold dark matter paradigm. So thank you very much.
Thank you for the introduction. Can you hear me? Okay. So thank you for the invitation here, and thank you for the kind introduction. What I'm going to speak about today is the formation of dark matter halos in the cold dark matter scenario, but the, let's say, true title under this more effective one is actually The Origin of Assembly Bias. Don't worry if you never heard this name. I will clarify what is meant by that. So, for those who work on very different fields, you probably saw this picture thousands of times. So the current leading cosmological model, which is based on standard physics, actually includes some elements which are not well clear what they are. And these objects, like dark matter, basically explains how galaxy clusters and the region surrounding galaxies are held together through gravity. Plus, there is an even more mysterious component that's been dubbed dark energy, but the name is probably nothing more than a placeholder that explains a strange phenomenon, which is the fact that gravity, as we all know it, is such that if I grab an object like this key, and I throw it up in the gravitational field of the Earth, the gravitational acceleration is such that decelerates the objects and brings it back to my hand, unless I actually manage to throw it at an incredibly high speed, which I'm not able to. But if this key would be a galaxy, what we actually see is that the galaxy would actually recede from my hand in an accelerated way. So what we would probably call on Earth an anti-gravity or something like that. And so the reason for that is still unclear. There are a number of missions, including the Euclid mission that you all know very well for sure here, that are meant to clarify that. Now, what this talk will be about is not at all about dark energy, but we'll focus on dark matter, that we have plenty of evidence for its existence, and this evidence is basically only due to gravitational phenomena. We know that we need dark matter to explain the galaxy dynamics in galaxy clusters, rotation curves of spiral galaxies. If we want to explain in detail the power spectrum of temperature anisotropies in the cosmic microwave background, we also need dark matter. And we see through gravitational lensing actually that the matter distribution extends well beyond the visible part in galaxies. So whenever we speak of a galaxy, which is the visible part of cosmic structures, we should imagine a kind of roundish extended halo of dark matter in which the galaxy is embedded. So what the talk of today is about trying to understand a bit better how these halos surrounding galaxies are formed through the process of gravitational instability, And in particular, what is the crosstalk between the formation of these objects and the large-scale structure of the universe. For a long time, this very nonlinear phenomenon, which is halo formation, has been regarded and studied as independent from the presence of the large-scale structure. Most of the models are based on spherical approximations and basically just describe the presence of a single perturbation in an otherwise homogeneous universe. What we will try to do is to go beyond that and try to see how the fact that there is nonlinear large-scale structure around this collapsing perturbation is going to influence their final state and their process of formation. Now I have a kind of rather trivial questions that though put some fundamental questions in the back of your mind. So imagine, so this is one of these dark matter halos in a high resolution numerical simulation. And you see in this cold dark matter scenario we believe in, it contains thousands of very dense substructures. So when you see yellow here means very high density, when you see dark means very low density. And now you want to decide where is the boundary of a dark matter halo? What does this mean? And here in parallel, sorry, this morning the internet in my room wasn't working. I wanted to replace London with Paris actually, but I couldn't. So this is London. And there are the different zones that, based on which the ticket of your transportation changed price. And now deciding where London ends is basically a similar problem of deciding where a dark matter halo ends. So there are some criteria which is around. One of the most common one that you find in textbooks and so on is to define a virial radius, that in this case would be this white line, that basically tells you what is the radius at which the mean density inside is equal to a given overdensity with respect to the outside. And based on simple analytical model of collapse, you expect that region to satisfy the virial theory. There are other more complicated definitions. Most recent one is what's called the splashback radius, that in this case would correspond with dashed line there, which has basically to do when a small substructure falls into the halo, will actually reach this pericenter and then splash back, like when you throw a stone in water, to some distance, and you expect that the distance it should reach after the first pericentric passage, it would be defined in this splash. In some sense, it defines the bound region associated with this overdensity. So first question mark, what defines the end of a halo? The second question mark is, where do halos form? Let's do a simplified version. Here is a one-dimensional random field that is supposed to mimic the overdensity in the universe. So here you have distance, some arbitrary units, and here is this overdensity field that is basically a random field with some particular power spectrum. And now you want to put your finger in the regions that will give rise to halos, let's say, of this size. So that was one of the most obvious problems to tackle in the early times of the CDM formalism. And what people came up with is this following idea. Well, if I'm interested in halos that have this mass, so they correspond to a particular length scale in the initial conditions, I could try to smooth this random field on this scale, and you would obtain something like that. And a reasonable expectation is that the halos might form at the peaks of this density distribution, where probably gravitational attraction is such that you will have a net inflow. So this led to what is now called peaks theory. I tried to dig back in the literature to find out actually where this started, and found that it's actually quite difficult. What I found, maybe Nick knows more, is that it was already discussed in our old paper by Doroskiewicz in the 70s. In Peebles' book, the last case structure of the universe is mentioned in one particular page, but no one refers to anything before. So I don't know if that was the start or it was so obvious that no one had to mention. But it became very popular, actually, when Nick used the idea basically to explain why clusters of galaxies had higher clustering amplitude than galaxies. And after that, it has been used many, many times, even though there aren't so many tests of this hypothesis against numerical simulations. There are a few by Carlos Frank. I did something during my first postdoc in Jerusalem, but we will get back to that quickly later. So it's a bit unclear what we can define the boundary of a halo. We have a rough idea where they could form in the initial conditions. Now you can ask, how do they form? And I guess most of you took at least a basic cosmology class. And in a basic cosmology class, you are taught the spherical top-hat collapse model. That basically says, imagine that a halo is a spherical overdensity in the initial conditions, which just expands with the Hubble flow, but is slightly overdense compared to the rest. And now, depending whether your teacher wants to discuss that in the frame of general relativity or in Newtonian physics, you either invoke Birkhoff-Jepsen theorem or you just do a Newtonian calculation. You find out exactly the same solution. What you find out that your initial sphere will expand, but the expansion will be slowed down by self-gravity if the overdensity is dense enough. It will reach a time at which the radius reaches the maximum radius, which is called the turnaround time, will collapse afterwards, and then you expect that the spherical symmetry will be broken by, well, because nothing is really spherical in nature, so you will develop some random motion inside, which will stabilize the structure at a given size. And what is usually done is to remap this in terms of the linear density field, so the one that follows the linearized fluid equations for growth, and you find out that this collapse would happen when the linear overdensity would be over the unity. So we learned, or at least this is the conventional view, that halos should form at peaks of the initial conditions and should collapse when the linear overdensity of the peaks should get toward the unity. What all this picture neglects is the fact that there exists a Lasker structure of the universe around the single perturbations. Here, for instance, is the result of the 2DF galaxy redshift surveys. What you are seeing here is kind of a two slices of cake seen from above. Each dot here is a galaxy, and you see that galaxies in the universe are not really randomly distributed. They follow filaments, they trace voids, or regions with almost empty or bright galaxies. And all this complicated sponge-like network has been called the Lasker structure of the universe, or in a more pictorial way, the cosmic web. Now, if you run a cosmological simulation in which you just deal with gravity, what you end up from a Gaussian random field initial condition, you end up producing a similar structure in which the dark matter halos we were speaking about are these very dense structures, and then you see again this cosmic web. So let's try to summarize what is the conventional wisdom about the collapse of dark matter halos. As we said, the virialized part corresponds to a mean overdensity of roughly 200 times the mean density of the universe. Halos form out of linear density peaks, and they form at the time in which the linear overdensity is mooted on the halo size over the unity. Another, or at least what you find in certain test books, is that the mass accretion history of the halos reflects the density profile around the peaks out of which they form. And halos keep accreting matter all time because there are always new shells that are falling into them. And if you think in terms of the Lasky structure, the typical sentence is that mass accretion takes place along the filament. So the idea is that mass flows along the filaments towards the knots of the Lasky structure. What we are going to see, actually, that is not really true in all cases. And so conventional wisdom should be challenged. So nowadays we have a oracle in our everyday life, which is Wikipedia. So let's see what Wikipedia says about conventional wisdom. Well, conventional wisdom is not necessarily true. It's made of ideas that are convenient, appealing, and deeply assumed by the public who hangs on to them even as they grow outdated. So let's see if some of these ideas actually are grown outdated or not. This is interesting, actually. It's often seen as an obstacle to the acceptance of newly acquired information, and as a property which is analogous to inertia, that basically slows down a change of paradigm because the person wants to hold to their certainty, which sometimes is the outdated conventional view, and so must be overcome by legitimate revisionism if there is enough evidence. So I want just to show quickly some suggestions that this paradigm might fail, and then going in detail into one particular aspect that actually led us to think that many of these points should be revised. So the first question is, do halos really form out of peaks in the initial conditions? So here you just do the test. You run a numerical simulation. You identify halos in your final output, and then you trace them back in the initial conditions. So these red dots are all the particles that are found in a halos of over density 200 in a ratio 0. And what you see below are density contours in the initial conditions. And in particular, this yellow one would be the contours associated to the spherical collapse model. And what you find, there are some halos which spot on sit on peaks, and some others that actually don't. They tend to be more subtle points in between peaks. Now, if you reduce the smoothing scale, you actually find a peak also there, but it's on much, much smaller scale. So it seems that there are some regions that manage to accrete much more matter than expected by the spherical collapse model. And what typically happens is that if you look at very, very massive halos at a given epoch, they tend to be of this kind. If you go down in mass, and for the pundits you go below m star, you tend to find mostly halos of this kind. So another thing that you should challenge is that the initial conditions of halos are spherical, which actually they are not. They typically have axis ratio 0.8, 0.8. But if you look at those who don't come from peaks, they are even more prolate. So the axis ratio is more 0.7, 0.4, actually. And another thing you find is that this shape correlates very, very strongly with the shapes of the linear tidal field. So this led to the development of alternatives to the spherical collapse model. There is the very well-known ellipsoidal collapse model. I see Dick Bond sitting in the audience. Is this Bond? And the idea here is basically to take into account the effect of the Lasky structure on the collapse of a halo as torque in the initial condition. You start again from spherical initial conditions, and what happens that 1 second after the torque starts acting, you end up with an ellipsoidal shape, and then you will have to deal with 3 different collapse times for the different axes. And recently we have extended this to what we call the ellipsoidal square collapse model, in which we just start from an ellipsoidal region rather than a spherical region. In this case, you have 2 competing effects. You have the external shear that wants to make you ellipsoidal in one way, and the internal shear due to the fact that you're initially not a sphere that actually counteract this effect. And what it happens actually that the three axes come to collapse at the same time in the end. Anyway, you try to compare this with numerical simulations, and you will see you will find immediately a problem. But when you do that, you actually find that the agreement with simulations actually basically follow these steps. This is the model who agrees better with simulation. This is slightly worse, and this is much worse. But what I want to talk to you about today is a phenomenon that actually triggered our analysis of how a halo really collapses. And this phenomenon is known as halo assembly bias. So before going into this detail, since you might not work on related fields, I want to explain what is a correlation function. So now imagine that you have a distribution of points. And these points could be galaxies, could be even a cluster of galaxies. Doesn't really matter, as long as the only information you want is the position. And now you want to treat this statistically, so you average over a large volume, and you ask yourself, what is the probability of finding one object in an infinitesimal volume? And it goes by itself, the probability of finding one object is proportional to the density of the point process times the infinitesimal volume. Now you can ask, what is the probability that if I put two volumes which are linked by a rigid stick, I actually find one galaxy in each of the two volumes? And the answer you can write as what you would find if the distribution would be completely random. That would be simply the product of two of these, so n squared times the two infinitesimal volume. And then there could be an excess or a defect with respect to that. And this excess, you call it two-point correlation function. So it's a measure of galaxy clustering. It tells you if galaxies tend to be more clustered or less clustered with respect to random when, as a function of separation. So now you can take a numerical simulation and compute this two-point correlation function as a function of distance for halos of a given mass. And the answer you find is this black line here. Now, you keep the halos of the same mass, but you create subsamples by looking at another property. And this other property could be the age of the halos, that we will see later how you can define an age unambiguously. But just assume you can do that. And you take the 20% older halos at galaxy scales. If you do this at cluster scales, actually the phenomenon reverse sign, but let's do this at galaxy scales. So the older halos two-point correlation function now is this. And if you take the younger 20% of the halos, you will end up here. So you see that how strong halos are clustered, which you can translate how they are located in the last case structure, correlates rather strongly with their age, so on the way they formed. And you might ask yourself why you care. The issue is that apart from understanding these issues of collapse, there is also a practical implication. Halos host galaxies, and we study galaxy clustering to inform cosmological models. If this phenomenon actually affects the cosmological measurements, you need to take care of that. And one of the big questions is this as strong as it is for halos for galaxies? And that depends on how tight is the association between galaxy properties and halo properties. So, I'll skip that, I'm speaking too much. And another interesting phenomenon is that some years ago, Faltenbacher and White found out a puzzling thing. If now you split the halos instead that with their age, with some internal dynamical property. And in this case is actually the velocity anisotropy parameter. So what is the ratio between the tangential velocity dispersion of the matter in the halos and the radial velocity dispersion? you find a strong signal as well. So those with high anisotropy parameter cluster low, and those with low velocity the anisotropy parameter cluster high. So now you see that the way matter actually orbits inside the halo seems to relate to the large-scale structure of the universe. And this was very puzzling, and there was no known explanation to that. And I hope I convince you that now we know one at the end of this talk. So all these phenomena, why there is assembly bias, and why the internal structure of the halos seems to reflect the fact that there is a cosmic web. Why is that? So we decided to actually study the whole process with very high resolution simulation, which is not what you're going to see now. Now it's a very low resolution simulation just to make a quick movie to give you an idea. So we wanted to study how halos form in a simulation. And now there is a problem. In a simulation, nothing is so idealized like the models I spoke about before, the spherical collapse, ellipsoidal collapse models, in which you have a clear ellipsoidal shell that move around. Since cold dark matter has power on all scales, you have somewhat relate what really happens in a simulation, which are the little movies there, and a model. So what we did here, we basically compute the inertia tensor of all the particles that form a halo, and compute its principal axis and so on. And so what you see here as ellipses is actually the projections of the inertia tensor of these particles, which are painted purple. And so we use this as a proxy for what an analytical model would describe as halo formation. And here you see the volume, physical volume occupied by the shell, and you see it does more or less what the spherical collapse model was suggesting. The halo is spun, turns around, and then kind of virializes some scale after oscillating around that scale for a while. So if you want to define a collapse time here, what can you do? We actually follow the advice of some famous physicists, and now the question is, do you recognize who this guy is? Is actually Clausius, who was a professor in Bonn, who actually is the person who first wrote down the virial theorem. And one of the conditions for the validity of the virial theorem is that the volume in which your particles are confined is stable over time. So what we decided to do is to define the collapse time as the first time at which the integral of the volume of all the times later is actually equal to 0. Of the fluctuation, sorry, with respect to the mean. So here you can get two halos of the same mass, and you find that for some cases, you see the turnaround happened a long time ago, but the shell is still collapsing nowadays, and some other halos in which the turnaround happened a bit earlier, but then the shell was stable for more or less 70% of the life of the universe. So in this case, our algorithm would say that this is the collapse time, and for the other object, you actually have to go a bit in the future to find the collapse time. And what you can do, you can build an histogram of collapse times for halos of the same mass. And it will look like this. Here it just collects the tail that will collapse in the future from today. And now, we decided to do the following thing. We decided to focus on a small set of extreme halos, some which actually are not collapsed yet nowadays, and some that collapsed in the deep past. You see around 20–30% of the life of the universe, according to this criterion, and try to see if we see differences in their properties. First of all, what we checked is that when we do this classification based on old and young with this criterion, if we find assembly bias. And actually we found a very strong assembly bias. Is one of the properties that actually give the largest separations between the older 20% and the younger 20%. And with this, we came up with what we call the ZOMC project. We study how does the environment regulate the growth of halos and galaxies. So we got some praise time for that, and we used it to run a series of extremely high resolution simulations, both dark matter only and then with hydro, to see what happens to galaxies into them. So here you can see two of these halos. This is one, so whatever you see a name that starts with the S, in our language, we call it stalled, which means one of those who collapsed early on and never changed afterwards. And those who start with A mean accreting, which means not collapsed yet. And by eye, you don't see much of a difference, apart than maybe here there is more substructure. So what you can now do, and to look at the radial phase space density of the particles inside the halos for these two halos. So I don't know how much familiar you are with this. So here you have the distance from the halo center, and here you have the radial velocity component from the halo center. And what you see basically in this region here is the velocity dispersion inside the potential well of the halo. Then you see a clear infalling branch here, and you see some strange spikes here, actually receding from the halo. They are positive radial velocities. What are those? Those are streams from the substructure which has been stripped during the first pericentric passage. Okay, so if you would run a movie, what this would do would actually stretch in time and become closer and closer to the zero axis. So I repeat, three components: the virialized part of the halo, an infalling branch with rather limited velocity dispersion, and these outgoing streams. What you see here as a white line is actually the overall average velocity of the particles in the halo as a function of radius. And you see that there is a net inflow here. So this object is indeed accreting mass. And if you look at the density profile of this object, at Reshi 0 and Reshi 1.5, it has changed quite a bit, consistent with the fact that mass is still inflowing into that. Now we move to an object of those we call stalled. And look at the phase space distribution in this case is very different. You see that there is no net, apart from this single substructure, infall velocity there, so there is no accretion of matter on this object. So of course there are particles which are infalling, but there is an equal number of particles which are outflowing. And so this infall branch is not really visible here. And also velocity dispersion in this region which is out of the halo, that's actually what you would call the virial radius of the halo, and this is the splashback radius of the halo, is much bigger than in this case, suggesting that this halo is embedded in some kind of massive structure, which is unclear what it is at the moment. The most surprising part of all maybe is this though. If now you plot the density profile of this object at Reshi 0 and 1.5 is actually completely identical within the virial radius of the halo. The only difference you notice is that the mean density of the universe has decreased over time. Okay, so this confirms that our classification based on what we defined as collapse time reflects different kinds of structures. Objects which are still accreting matter nowadays through a clear accretion flow, and objects which are kind of in a stationary state that no net inflow of matter is present. So a kind of revelation comes when you actually, instead of plotting phase space, you plot how are these halo in configuration space. And what you find is that halos of the first kind are not in the large-scale structure, which are surrounded by rather thin filaments compared to their virial radius. While objects that we call stalled, so those who don't actually get any net accretion, but have this huge velocity dispersion in the environment, are actually halos which are invariably embedded into very thick filaments, which are much thicker than their virial radius. So this already tells us that the large-scale structure is somewhat affecting the way a halo is assembled. We can actually have a better unifying view of the last two plots by color-coding particles. By color-coding particles based on their radial velocity. So here, whatever you see red is actually outflowing from the halo. Whatever you see in blue is infalling to the halo. And the whitish region is the turnaround radius. And what you see that when you are in a knot, you actually indeed accrete through the filaments, as the standard law common wisdom was saying. But for the vast majority of halos or galaxy mass that we said of the stall type, this doesn't happen. What happens actually that the only accretion you have doesn't come from the filament, it comes from the direction perpendicular to the filament, so the matter that from the voids try to reach the filament and then infalls onto the halo, while there is no net accretion at all. Actually, all the material along the filament is running away from the halo. I had some more detailed plots for this. I'm not sure I have the time to go through that. Well, basically what we did here, you go back to the initial conditions, and this is all the material in the initial conditions that form the halo. This is one accreting halo. And now we put a cylinder here, and we color code the particles inside the cylinder based on their position in the initial conditions. And now we look where they are at redshift 0. And then we plot for some of them the actual radial trajectories that they did. And what you find are, of course, those which are in the middle of the perturbation end up in the virial radius, and so they have been oscillating within the halo many times. And those which are around the boundaries are actually still around, turning around and falling back onto the halo along the main filaments that feed the halo. So this is a halo that confirmed the standard viewpoint, but if you look at stalled one, you actually see a very different thing. Let's focus on the bottom panel, same thing. So initial conditions, small cylinder, paint green, those which are the boundaries on this side, paint red, those are the boundary on the other side. See where they are in the present day. And you see that they actually spread all along the filament, and they reverse the left-right situation, meaning that they have shell-crossed. And meaning they have shell-crossed when they actually took part in the formation of the filament. So these structures, this material, collapsed along one direction to form the filament, but they're never accreted to the halo. It's actually running away in opposite direction on the filaments, and you can see their trajectories actually accelerated away from the central object. The reason is that they actually fall in onto the two big clusters that create the origin of the filament. In the famous paper on the cosmic web, one of the conditions to form a strong filament is that you have two massive structures whose deformation tensor are sufficiently well aligned, and this is the condition for which you form a strong filament like that. So it means that somewhere up and somewhere down, there are two massive structures, and actually these particles are actually flowing towards these two structures. So what we want to see now, if there is any effect on the internal structure of the halos. And so we go back to this anisotropy parameter that was used at Faltenbacher and White. And what we find that stalled and accreting halos have completely different anisotropy profiles, in which accreting halos are actually dominated by radial motion, and stalled halo are dominated by tangential motion. You might wonder why, and the reason is that this reflects the way matter accretes onto the halo. In the normal accreting halos, the accretion is mainly around radial orbits along the filaments, while when a halo is stalled, what the matter really does, it first flows onto the filaments, it starts orbiting in the plane perpendicular to the filament, and somehow some of this material manage to spiral down to the center halo, and so all the matter that influences on the stalled halos arrives on tangential orbits. And this remains all the way to radii of order 10% of the virial radius. So there is a way to actually link this to the initial conditions and exclusion set theory and so on, but I don't have the time to go through that, so I will actually skip that. And what I want to speak about in the last minutes is what happens when you put gas. So now we rerun simulation for this set of halos, adding gas, and what you basically find is that at the level of halo radii, the gas accretion actually matches dark matter accretion, so it's stalled for the stalled halos, it's not stalled for the accreting halos. But if you care about the central galaxy, this difference is not there. And the reason is that most of the gas gets shock heated once accretes into the halo, and the cooling time is so long that basically what after cooling rains onto the central part of the halo has no memory what happened in the outer layers of the halo. So for what regards gas accretion into the central galaxy, the connection to the cosmic web is rather lost, while what happens at the level of virial radius in the inflow of gas reflects what happens in the dark matter. Anyway, you might look at what is the morphology of the central galaxies you get in these halos. And this is an example for one accreting halo and one stalled halo. And you see in both cases at redshift 0, you see some beautiful grand spirals. So if you were hoping that this property of being stalled or being accreted would reflect in some strong properties of the central galaxies, you're going to be disappointed. But what you can certainly notice is that there are some regular differences between these different galaxies. One of them is actually the thickness of the disk. Accreting halo and stalled halos, well, this is the gas distribution. I have to show you the stellar distribution in which you clearly see the difference in thickness. The stalled halos has roughly twice the thickness in the disk of the accreting halo. And the reason is that the stalled halo had a long time through which substructure could actually puff up the disk, and also has a much older stellar disk, as we will see in a second. This was just to show that the galaxies we get actually have pretty good agreement with observational properties at redshift 0, but again, I have to go quick. And here it's a bit complicated plot, so let me guide you through this. Here you have the circularity parameter of the stars, which means is the ratio between their angular momentum component along the total angular momentum of the galaxy and what you would have if you were on a circular orbit. So you expect this component to be around 1 here, and here you have the formation time of the different stars, and here just as an example you see what is the star formation history of these galaxies. And what you see on top is 2 of the stalled halos, on the bottom 2 of the accreting halos. And you see a regular pattern here that the spheroidal component formed first in both of these objects, and the disk follows. But the disk start forming much, much earlier in the stalled halos with respect to the accreted ones. Here you start forming the disk at more or less 2 gigayears age of the universe, while here you start around 7 gigayears. So the only two properties, all the rest we checked quite carefully, all the rest we couldn't see any systematic difference. The only two properties we could link between the central galaxies in our simulations and where they are in the Lasky structure was the thickness of the stellar disk and the age of the stellar disk. The last thing we looked at is actually what happens to satellite galaxies in the two different configurations. And well, here just shows what typically happens to a satellite galaxy when it's destroyed. That is not really important. What is important is how the satellite galaxies accrete onto the halos. And once again, it's very similar how the total dark matter was accreting onto the halos. So here you see a plane, and this plane has been chosen in such a way it contains the largest and the smallest principal axis of the tidal field. And in the case of the filament, which is this axis run through the filament, and this axis is perpendicular to the filament. While this is the case in which the halo is a knot of the Lasky structure. And once again, you see that here the satellites accrete onto the halo along radial orbits. So these are trajectories of all the satellites in the simulation, and some of them are highlighted in colors. While here, when you are in the filament, you see that once again, the satellites, first of all, don't come from along the filament, but actually come from the perpendicular direction, orbit a bit within the filament before falling onto the halo, and sometimes they even run away along the filament. If you now plot the radial velocity distribution of the satellites at the moment in which they are accreted onto the halo, you find very different probability density functions for the halos in filaments and in knots. And you see that the radial velocity component is very strong when you are in a knot, again confirming that the material falls onto the filaments, while it's not the case when you are in a filament. If you run a KS test here, you find, I remember we did the game, the significance is 10 to the minus 300, that these actually come from the same distribution. Now you can ask yourself, this is at accretion time, is this property preserved at redshift 0 such a way that I could actually hope to measure the distribution of the satellites and infer from that whether I sit in a filament or in a knot, so whether I'm in a stalled halo or accreting halo? And the answer is yes, but. So now, sorry, is the dashed distributions. You see they are more similar at redshift 0, but they are still sufficiently different that if you run a KS test, you could distinguish the two, although you need a large number of satellites. And nowadays, we basically have the satellites in the Milky Way and Andromeda, for which we could do similar tests. So the last plot I want to show you is an interesting speculation. So a couple of years ago, Marius Schouten and Carlos Frank used proper motion measurements for 10 of the satellites, of the classical satellites of the Milky Way, to infer what is their velocity anisotropy parameter. And they came up with this confidence region here, this shaded cyan region. Then they took one of their simulations, N-body simulation, over which they ran some semi-analytic model. And they selected out of that Milky Way-like galaxies and measure what is the velocity anisotropy parameters of their satellites. And the distribution in the CDM scenario is this magenta line. And based on this plot, it looks that the Milky Way is rather exceptional in the CDM scenario for having this kind of velocity anisotropy parameter. However, what we did, we actually repeated the measurement using our high-resolution simulations and dividing the halos based on whether they are stalled or accreting, as we saw before, that this influences what is the beta you're going to find. And here we just plot 4 of these halos, and you see that those which are stalled, actually, they are always in the ballpark of the Milky Way, that those who are accreting are actually more similar to the peak of CDM halos. So based on this, based on the fact that the thickness of the disk on the Milky Way seems to be a bit on the high side, and also the stellar population seems to be rather old, we could try with not very high confidence to speculate that all this is pointing towards the fact that actually the Milky Way could be what we call the stalled halo, so living in a strong filament of the Lasky structure. I have something about what we are doing now, but I'm going to skip it. So, putting down conclusions, I think we uncovered the original assembly bias for galaxy-sized halos, and this has to do with the way the accretion of dark matter onto them is influenced by the Lasky structure of the universe. Basically, the rare galaxy-sized objects which are nowadays still not of the Lasky structure of the cosmic web fed by thin filaments are actually following the standard law, while the vast majority of halos which are nowadays embedded in thick filaments, they actually don't have any net accretion, and for that reason they have a very different clustering properties. So the key is that nonlinear elements on the cosmic web prevent halos to further grow, and mass accreting halos sit in the knots, while stalled halos in the filaments, and this is basically the physical origin of the bias. The interesting part is that this different way in which the matter infall onto the halos sets up the internal kinematic structure, and gas accretion reflects this on the halo level. But unfortunately, due to the fact that it takes a long time for the gas to sit down in the center where the galaxy sits, the effects are much, much mitigated there. And the only properties we could find in our simulation that suggested a difference is just the stellar age and the thickness of the disk. More interestingly, from the observational perspective, it seems that the velocity anisotropy parameter of the satellite galaxies reflects actually the assembly history of their halos. Thanks.
Questions?
I actually have 2 questions. The first is about mass dependence. In the very last figure that you showed, the peak of the distribution of CDM was all for accreting halos. Does that depend on the mass of the galaxy that we're looking at?
I can't really answer, in the sense that the high-resolution simulations we ran, they are all in the same fixed mass range, which is the mass range that should host L-star galaxies nowadays, so a bit smaller than the Milky Way, actually. What we are doing now, but I don't have conclusive result, is actually extending this range by using constraint simulations. And it seems that as long as you don't move too much far away from, let's say, Milky Way mass, and so the results are exactly the same. When you start going on group on cluster scale, basically there are only accreting halos. Okay. The stalled ones don't exist because you don't have filaments which are so thick, let's say so massive, to embed a cluster like.
Well, I'm more interested in the small galaxies. Okay. And the second is about conventional wisdom. So for someone who doesn't really work on cosmology, is it still okay to give this sort of picture to a student who want to understand a little bit on, how galaxies and halos form? The basic picture that you started with.
Well, I think it is. Maybe with the caveat that it basically holds true only for the very massive halos which are present at a given epoch. When you go to the smaller objects, what we call below M star, they are kind of survivals, okay? They just use the volume which is left that has not been used by the bigger ones, and in some sense they are special, and this speciality is reflected in this more complicated formation phenomenon. So I don't know. I think, for a generic class, there is nothing wrong in teaching the spherical collapse model. I think it's a bit naive to expect that that actually applies to all possible structures.
I want to add a comment. I would argue that from an observational point of view, if you look at very massive galaxies, then they tend to all be ellipticals, so it's okay to assume that only mass drives the morphology of the galaxy. If you look at intermediate mass, you have ellipticals and spiral at the same mass, so obviously mass cannot be the only relevant parameter. So in that sense, we should change a little bit the paradigm, because we can't explain morphological diversity with mass only.
So you mentioned the effect of assembly bias on disk thickness, but you didn't say anything on the morphological mix of galaxies, and especially about, do you have elliptical galaxies in this sample of simulated objects?
Okay, so as you well know, running very high resolution zoom-in simulation is quite expensive. Each of these runs takes several months on a big supercomputer. So our sample is actually pretty small at very high resolution. We are speaking of 7 simulations, something like that. So out of these 7 simulations, we mostly have nice disks and a couple of objects which I don't know you want to define morphologically. They are basically big bulges with some weird rings around, those small disks around. Now, our mass scale was pretty low. I can't say anything about the formation of elliptical galaxies based on that.
Okay. I have a second question, if I may. It's the other name for assembly bias in observations is galaxy conformity. Mm-hmm. People have invoked that a lot in the literature. And there is a debate about whether this galaxy conformity is real, and whether it is real up to tens of megaparsec scale. So what's your take on this?
Okay, so depends exactly what you call with galaxy conformity. What we tend to see in our simulations is that neighboring galaxies to our, let's say, main galaxies tend to have similar properties, but again, the sample is 7, so I don't know what, you can't do correlations there. The satellite central conformity seem to be present as well, but all the satellites are quenched in the simulations, all of them. So I don't think we can use our simulations to draw any conclusions about galaxy conformity. The issue in the literature is mostly how robust of a statistical treatment you use to draw a conclusion about that, and I wouldn't like to take a public position on that.
So I want to speak to conventional wisdom. I think you're talking about mid-80s conventional wisdom as opposed to the true wisdom, which was Bond and Myers. sorry, but
actually,
because
I'll let you finish.
That's
but-
mass peaks and not density peaks. So I think it's been so misconstrued that in our most recent paper on this, I decided I'd better put the mass dash peak in so that people got the correct vision. So the cases that you found, I think, are well understood within the peak patch model, even though you would have this situation where the central point looks like itself it isn't a density peak. But if you do it on larger scales, it would find that entity. So then the other feature, and I think this would be a really interesting measurement to do, you may have already done it. With assembly bias, it's like a second parameter, but there are obviously many tertiary and so on parameters. So probably the most important one in many respects is the anisotropic strain, anisotropic tide, anisotropic shear that's in the initial conditions. So an interesting thing to do is to determine, we called them EV in Bonn and Myers, would be to actually make those measurements for your two high-res sims, because EV will be negative, or sorry, really extreme for the one that's shearing away on the filament. And that doesn't mean that it wouldn't capture that the object formed there, but that would explain the flow patterns and would do a lot in order to really, in my view, explain your assembly bias history in terms of one parameter, even though the really good way to do it is to do multi-scale, like two-scale things, which is, in a sense, sort of what that's doing. Anyway, that's just a comment about the new conventional wisdom, which is vintage 90s.
Okay, so let me speak in my defense of what I call conventional wisdom. So conventional wisdom in the talk was meant what you find in textbooks nowadays. Okay, this is what a student who enters the field is exposed to. I had a few other lines in my original, the first time I gave a talk like that. I actually had something mentioning Bonn and Myers. Had to go through a long discussion with someone in the audience that didn't want that to be conventional wisdom, so I simplified now that. But, so the idea was you take your favorite textbook or cosmology, this is what you would read about halo formation. So, I agree that, well, the multi-scale is the key there. Now I had to skip for sake of time, but in the same papers we actually go through an excursion set explanation of this, and we find a way to incorporate all this. And the way you incorporate all that is to do excursion sets not only with the density, but to do simultaneously density and ellipticity of the tides. And what you find that the two kind of halos separate totally in that plane. And basically, if you say even a very simple spherical accretion model, in which you say you can't accrete if the ellipticity is above a threshold, it works beautifully. Actually, it gets the mass accretion histories of the halos very well. And what we are doing now is actually we are running constraint simulations on multi-scales just to actually impose points in the trajectory of the excursion set and see what kind of mass accretion histories we get. And actually we are finding, even though this is preliminary, that ellipticity is not enough. Actually, even the prolateness of the density of the tidal field influences the final product of halo collapse. So I think it's in line with what you are saying. With the EV,
Doing high-res sims in the 90s, we had two scales for the strain, and that really does make a difference. Which is, I think, what you described.
So first of all, thank you for your beautiful talk and your beautiful results, and very clearly explained.
Thanks.
And it's interesting to do observational tests on this beautiful idea of assembly bias. And one observational test that Radek, Wojtak, and myself have done in 2013 with marginal significance only, was that we think we found signs that we did mass orbit modeling of galaxies traced by their satellites, the SDSS, and there are marginal signs that the old galaxies, which we call the red galaxies, have halos that are more concentrated than the blue galaxies of the same mass, whether it's stellar mass or halo mass. And again, it was maybe 1.5 sigma significant. Interestingly, compared to your results, our galaxies are red, the red ones tend to be ellipticals, etc. Okay, whereas you only see spirals, but it's very beautiful that you see grand design spirals compared to tightly wound spirals. So I was wondering whether you've tried to correlate halo concentration, which is easy for you to measure, with galaxy age.
Okay, so we are aware of your work. Is actually referred in our paper as an example of how observation could actually test all this scenario. I'm sorry I'm saying the same thing constantly. At this high resolution, we have actually too few simulations to do any meaningful correlation. The way to do correlation is actually to run big cosmological runs in which we will never have the resolution to see the central galaxy or to discuss any morphological property of the central galaxy. But if you come up with some other correlation that could be used as a proxy for what you want, we certainly have all the simulations that would be needed for that. We are thinking of increasing the sample, but again, I mean, if you need 5 months for one single run, you can never reach, the thousands you want to have a robust correlation.
Okay, maybe one last question, Nick?
Yeah, great talk. I enjoyed it a lot. I wanted to make a sort of historical comment, because you mentioned the original peaks thing. Everyone had that picture of the wiggly line on their blackboard, back in 1982. But the conventional wisdom, the reason the calculation was useful was the conventional wisdom then was that the strange clustering of clusters, being much highly biased, was completely impossible to understand in the conventional picture. Peebles had just written a paper saying it required some special non-Gaussian initial conditions where maybe it was sort of like Gaussian, but it had to be modulated on large scales. And what the peaks model showed was that's wrong. It actually emerges very naturally from what we all thought were the most natural conditions. The other thing is, the success of that model, it was hard to test it at the time because the simulations were useless. My impression is it just works wonderfully, particularly if you think what's important is how does the structure, the distribution of galaxies respond to long wavelength modes and things. That aspect of it is very strong. Of course, you've got to paint on the gastrophysics and all of that.